great honor to present for you today. And my research is find drivable segments from road images using depth and RGB imagery. This is my presentation outline. Let me start with the research background. Deep neural network represents the cutting-edge technology in semantic image segmentation and have found extensive applications in the field of autonomous driving. Autonomous driving comprises four critical components: perception, localization, planning, and control. Within the realm of perception, deep learning is harnessed to enable the vehicle to detect obstacles and lanes. However, the substantial computational demands and real-time response requirements pose significant challenges for on-vehicle device. This challenge serves as a motivation for exploring techniques to merge information and streamline the model. In the scope of this study, the driving environment will be represented as distinguishable regions, drivable and non-drivable space. Additionally, an exploration will be conducted to determine the feasibility of reducing model size while preserving accuracy to facilitate deployment on vehicle devices. The primary focus on this investigation will center on two prominent neural networks, Deeplab V3 and UNet. There are three main problems. First, deep neural networks require a significant amount of computation power and memory size on vehicle computation unit. Additionally, more data sets normally mean better accuracy. There will be large amount of data set need to be processed by neural network to produce meaningful output. Lastly, neural network is unstable and sensitive to adversary perturbations such as image cropping, resize, light change due to vehicle vibration and road condition. Deeplab and UNet stand out as two widely adopted foundational models for image segmentation, while previous research have leveraged Deeplab V3 in conjunction with ResLate 18 for tasks like building extraction, road segment detection, and object detection. These studies have primarily focused on specific applications. However, they have not extensively addressed the key considerations of efficiency, such as model size and its performance. Moreover, their studies did not employ the depth images as input sources for their training and validation processes. The UNet architecture in Figure 1 comprises two parts: a contracting path to capture context and a symmetric expanding path that enables precise localization. There is a batch normalization added comparing with original structure per preferred paper. The contracting path is a fully convolutionary network consists of repeated 3x3 convolutions with zero padding. There is a rule after each convolution layer. Then there is a 2x2 max pooling operation with stride 2 for downsampling. At each downsampling step, the number of channels is doubled. The expanding path uses 2x2 up convolution that will have the number of feature channels. Each of the up convolution layer can calculate with the corresponding extracted low-level feature map from the contracting path. Then there are 2 3x2 convolutions followed by a array rule. The purpose of cropping is to handle the loss of border pixels in every convolution. At the final, there is a 1x1 convolution to map each component feature vector to designed number of classes. In total, the network has 23 convolutional layers, reducing the number of feature maps while increasing their dimensions. Deeplab family has been extensively studied since it was introduced. The use of Achor's convolutions, Achor's spatial pyramid poolings, ASPP, global pooling, and conditional random fields, CRF, brought about significant performance improvement. In my work, I used the Deeplab V3 Plus architecture, which removed the CRF post-processing layer while keeping the Achor's convolution layers, ASPP, and global poolings in the encoder and adding a skip connection to feed low-level feature from encoder to decoder. In order to deal with the different input image size, fully connected layers can be related by 1x1 convolution layer is in case of fully connection layer. But to make the model robust to different sizes of input images, the solution to deal with variable sizes the images is to train the model on various scales of the input image to capture multi-scale contextual information. Usually, a single pooling layer is used between the last convolution layer and a fully connected layer. Deeplab instead utilizes a technique of using multiple pooling layers called SPP to deal with multi-scale images. SPP divides the feature maps from the last convolution layer into a fixed number of spatial bins having size proportional to the image size. Each bin gives a different scaled image as shown in the figure. The output of SPP is a fixed size vector f times b. F is the number of filters, feature maps in the last convolution layer, and b is a fixed number of bins. The different output vectors are concatenated to form a fixed 4 times 4 plus 2 times 2 plus 1 times 1 in total and times 256, which is 5,376 dimension vector, then fed into the fully connected layer. There's a drawback to SPP that it needs to increase in the computational complexity of the model, the solution to which is Achor's convolution. Unlike the normal convolution, dilation or Achor's convolution has one more parameter called the dilation Achor's rate, R, which defines the spacing between the values in a column. The dilation rate of 1 corresponds to the normal convolution. Deeplab uses Achor's rate of 6, 12, and 18. The benefit of this type of convolution is that it enlarges field of view of filters to incorporate larger context without increasing the number of parameters. Suppose you have an input RGB image of size 12 times 12 times 3. The normal convolution operation using 5 times 5 times 3 filter without padding and the stride of 1 gives output of size 8 times 8 times 1. In order to increase the number of channels, we need to use 256 filters to create 256 8 times 8 times 1 outputs and stack them together to get 8 times 8 times 256 output. The whole operation costs 1,228,000. Hello? Yeah, okay. it costs over 1 million multiplications. However, in depthwise convolution, the convolution operation is performed separately for each channel using 5 times 1 convolution filters, staking whose output gives 8 times 8 times 3 imagery. The pointwise convolution is used to increase the depth number of channels by taking convolution of 256 1 times 1 times 3 filters with 8 times 8 times 3 imagery, which are stacked together to get 8 times 8 times 256 designed output imageries. So the whole operation takes 53,952 multiplications, which is far less compared to that of the normal convolution. My research objectives are to improve the limitations of Deeplab V3 to reduce computational time, but maintain similar accuracy and investigate its performance under noise and its computation cost vs UNet. In order to achieve the goals, I use a common pipeline developed including data loader with image pre-processing and augmentation, model training, model evaluate, and post-processing. The input to the model is images with depth information by pointwise, field steps, and RGB images. The backbone of Deeplab from ResNet 101 to ResNet 18, in order to reduce the model size, this will help to make it able to be implemented with limited computational capability on vehicles. The performance of my pipeline using my model will be compared to UNet, which is implemented per the paper, UNet convolutional networks for biometric image segmentation. I then compare the model to UNet in terms of computational cost, loss, and visual comparison of the outcome images. Cityscape's dataset has been used by my study. This dataset focuses on semantic understanding of urban street scenes. It has polygonal annotation customized for instance segmentation for vehicles and people. It has 30 classes which I perform data masking to make it into 2 classes, drivable and non-drivable space. It covers the various road condition images from 50 cities during different seasons of the year. In total, there are 5,000 images which with fine annotation and its corresponding depth images. It suits for pixel level semantic labeling, accuracy, precision, recall, and F1 score are used for success measurement. In my work, I add depth information by pointwise fusion depth and RGB images and make it to be the 4th dimension of the input images. For the backbone, instead of using large networks such as ResNet 101 proposed in the original paper, I use ResNet 18, which is much smaller version. This helps to speed up training and testing iterations. Furthermore, there's a smaller model has the advantage in terms of computational cost and deployment in edge devices in autonomous vehicles. I took the PyTalk official implementation of ResNet 18 and made modification by enabling dilated convolution and disabling striding and pulling in the last layer. This represents the last layer from reducing the width and height of the feature map. Thus, gives a wider feature map as the output of the encoder. which reduces the upsampling ratio in the decoder. Eventually, it improves accuracy in the final result. I then take the output of the first layer of ResNet 18 as low level feature and fed it into the concatenated with output layer of ASPP as suggested in the original Deeplab V3 Plus paper. This gives original low-level information in the decoder for better performance. For the experience and result part is shown in Table 1. I compared the scale and complexity between the two models and found that the Deeplab R18 has significant advantage with less parameters, less multiplications and addition operations, and significantly with less training time. For the training and validation process, it can be observed that there is overfitting issue during training causing high evaluation loss. I then implement image augmentation by perform image translation, rotation, and blurring. This helps to improve the model overfitting issue. To assess the effectiveness of the two training models, namely the UNet and the Deep R18, for this image segmentation task, I utilize the accuracy, precision, recall, and F1 score as performance metrics. Both models have similar performance as shown in Table 2. As Deeplab R18 has a smaller network than UNet and the autonomous car require fast in-depth inference speed, it makes sense to put more in-depth performance improvement effort into the Deeplab 18 model. 100 epochs of validation results have been reported here. Deeplab R18 achieves overall similar performance as UNet after both model performance converged. UNet performance converges faster than Deeplab R18 models. However, there are challenges associated with proposed approaches. It doesn't perform effectively in scenarios involving the segmentation of areas in close proximity to small objects or mistakenly identifies areas that should not be labeled as drivable. The primary difficulty in addressing this issue lies in the fact that these areas of concern share similar texture and color characteristics with the actual drivable road. Moreover, the model has been trained on images where these challenges areas have been allotted as drivable regions. The issue can be attributed to two key factors. First, the trained dataset lacks consistent masks for handling these intricate corner cases. Secondly, the model assigns equal weight to all areas, thus failing to differentiation effectively between them. In summary, the combination of depth imagery with RGB images as input to the Deeplab R18 model yields highly accurate results. When comparing predicted images with and without data augmentation, it becomes evident that the data augmentation effectively migrates overfitting issues, thereby enhancing the model's robustness. However, it's important to note that predicted images with augmentation tend to be misclassify the sidewalk areas and regions near posts or obstacles as drivable roads. Deeplab R18 offers superior accuracy while maintaining significantly lower computational requirements compared to other methods. Conversely, UNet exhibits some challenges with false negatives in certain regions. It struck us to distinguish between the texture of the road and that the vehicle hood. To address that, the study incorporated the output of the first layer of Reset 18 as low-level features, which are concatenated with the output of layer of ASPP. This approach enhances the speed of Deeplab R18 in comparison to the UNet while maintaining similar accuracy levels by reducing model parameter size and number of required multiplications. For my further enhancements, the focus will be on customizing the loss function weights, particularly for area close to the vehicle hood and obstacles, in order to further improve their model accuracy. These are my reference papers. And thank you very much for your listening.